My employer is in Vancouver, but I live in Montreal.
I take it you don't commute daily?
No. No, we Skype almost once or twice a week. Then I visit Vancouver 4 or 5 times a year.
What do you end up like paying taxes and like Social Security? You pay that in Quebec or you pay that in?
That's a good question. So nobody knew the answer until we tried and called the government. So the employer in UBC usually he pays some money for taxes for healthcare, and I cannot have that money. So but he still needs to pay it. So it goes into a big fund, and I don't have access. So I need to sort of pay my own health insurances.
Oh.
Yeah.
Wow. That's kind of brutal.
Well, it's not too expensive in Quebec.
Okay.
Yeah, I mean, because everybody's entitled for global, like, as a resident, you have your own health insurance for global, I would say, like,
Right.
It's just that anything which is not covered by hospitals, you need to pay.
So you're subsidizing like BC's,
Yeah.
healthcare BC residents,
Yes.
sponging off Quebec's.
Yes.
Good luck.
Yeah, but I benefit from Quebec's daycare system.
Okay.
Twofold. So it's more, yeah, speaking.
All right, welcome back. Our first speaker of the afternoon is Joachim.
Yeah, it's good.
Give it my best shot.
No, it's a very, very well-educated guest.
From UBC,
Yeah.
although not always present at UBC.
Yeah.
Please.
Yeah, so today I'll talk about weight cleansing. The main reason I'm not at UBC is because of money. I have 2 kids. So being in Montreal, I benefit from the daycare. It's $7 a day, it's much cheaper. But then there's also another advantage, is that we collaborate. I work with Ludovic van der Beek in UBC, and we collaborate with Europe. And he is exactly 9 hours lag with Europe, so there's no office overlap. In Montreal, I do have office overlap, so I'm in between everybody. So there is good science we can do. I can attend telecons, for instance. This is some of the challenges that we can address with weight cleansing. So basically, this is the energy pie of the universe. Dark energy consists of more than 2/3 of the universe. There's about 1/3, well, 20% of dark matter, 4% baryons. We know about nothing about energy. Dark matter, we know a bit more. We think we know how it clusters. It seems to be under the effect of gravity alone. Dark matter seems to form filaments and clusters in big voids. This is a slice from the Millennium simulation, and then other in-body codes out there reproduce this marvelously well. But that's just dark matter. We'd like to know where it is in the real world. This is in the simulation. It's obviously not the same. And then we'd like to know where the baryon goes in. So we think that, galaxies tend to reside in potential well of dark matter. But given a single dark matter halo, how many galaxies we should put in, then there's not only galaxies, there's also gas, warm gas, there's dust. So this picture is incomplete. Many answers are not found yet. So, and weight cleansing can help us doing that. Especially since the baryons that we count, so the galaxies and the gas and the dust, this accounts for about 60% of all the baryons which we predict in the model. 40% is missing. We'd like to know where that is, and weight cleansing can help us in that. It's sensitive to the baryons. So this is a brief overview of the talk today. So I'll do a brief review of gravitational lensing for non-experts. I'll talk about one of the recent cosmic shear measurement from the CFHT. I hope one of the bottom line you'll get is what you need for a good cosmic shear measurement. And then I'll describe a little bit my work with creating galaxy mock catalogs. And then we'll talk about some more science you can do with weight cleansing. So this is a picture of the Abell 1689 galaxy clusters. There's a few thousand galaxies, the bright yellow objects, which are in this cluster. This is a picture from the Hubble Space Telescope. And then we see arcs. I think you can see with the here. So these arcs are signs of strong gravitational lensing. So this means that we have, this is a system where you have a foreground galaxy cluster, and then you have background galaxy, which act as source. And the source gets deflected back toward the observer, forming these arcs. So this is, when you see arcs, it's called a strong system. And with the measurement of these arcs, knowing the curvature and the distance to the center, you can try to reconstruct what kind of mass can be responsible for this particular bending. And then with the mass, you can try to measure where the dark matter is. So this is a picture of the dark matter. The pink here would be the dark matter mass hidden to the eye, but they reconstructed just from the arcs. And so this is not cosmic shear. This is strong lensing. In cosmic shear, what happens is that you don't have access to the central part. So basically, what you look in the sky, most of the sky does not have a cluster. You have galaxies, but you don't see arcs. What you see is more something like the remaining of this figure, where you see galaxies. Some of them are close to you, some of them are further from you, and but there should still be a weight in the front and some lensing effect. So we try to reconstruct that. But the challenge here is that suppose you pick a galaxy here. You need to know if is it in the foreground, in the background, because the geometry tells you what kind of lensing you should get. And also, well, you don't see clear arcs anymore. You see shapes of galaxies, but then a galaxy has its own shape, right? It's often a disk, which you see from the side, so it has an intrinsic shape. And then you need to disentangle what's the intrinsic shape and what is the shear caused by the lens. And for a given galaxy, you can't. So what you need to do is to do statistics. So what you can do, for example, is to bin your image into annuli, and then over a given annuli, you can compute what is the average shape of each object, tangential and radial with respect to the center. And then you can just sum over the whole bin, and then you can have a plot or a figure of the cumulative shear with respect to the center statistically. So this is in the weak lensing regime. This is what I'm going to be talking about is the cosmic shear measurement. So it's complicated effect because it's not obvious by eye. This is a sample of 6 galaxies whose intrinsic alignment is all randomized. And then here is what the same sample with a slight alignment in this direction. And so by eye, it's really, really hard to tell. You really need to have a sample of galaxies to pick up the overall net alignment of the galaxies. And to do this measurement, you need to resolve the shape of each object. And with the shape, you can have the long axis, the short axis, and then with these ellipticities, you can construct an estimator for the tangential and radial shear. I wrote down a little formula here. So basically, this is the tangential component, this is the radial component, and W here are the weights, basically. So it tells you how well you were able to measure each galaxies, because some of them are fussy, some of them are far away, some of them are, you could have 2 galaxies which are sort of overlapping. It's hard to get the real shape. So you assign a weight. Thank you, LensMailer, for writing LensFit. It's an amazing tool. So basically, here, this is what you do. You measure the shape, you extract the axis, you organize all the pairs as a function of separation on the sky, like the bins I showed before, and then you correlate the shapes in a 2-point function. Here's a slide about how to get the distance right, because you need to know what's the lens, what's the source. If you just have a picture, you know the angles, but what's behind, what's in front, what's acting as a lens. So here on the left side, what I'm showing you is a spectrum, a typical spectrum of a galaxy, basically. So the blue line here is a spectrum of a galaxy at redshift 0. So it's just close to us. And basically, you have all these astrophysical processes which are emitting light out of the galaxy. And whatever happens with these high-energy photons here is that they get absorbed by neutral hydrogen, which is in front, like between the galaxy and you. So this is everything which is in front of 4,000 is absorbed. So the overall spectrum has a drop. And what happens if this galaxy is further away, it's redshifted. So you can see the same drop occurring at a different wavelength. And you can guess what's the redshift. And so here it's a 4,000. Here's the 4,000 break occurs at 6,000. So it's a redshift 0.5. And here the red line, the drop occurs at 8,000. That's a redshift 1, basically. So you have these spectrums. The problem with these spectrums is to make a measurement. The whole line here, it takes time, it takes resources, and also if the object is too faint, you can't get a good measurement. So what you can do to reach object at redshift 2, redshift 3, is to work with filters. So you do photometric redshift measurement as opposed to spectroscopic redshift measurements. So you can place filter, a green, a red, an I-band, or a Z-band filter in front of your camera. And then for each field that you look at, you place a filter, look at it, place a different filter, look at it. And then you can compare what's the intensity integrated over the filter. And then you try to look for the drop. And from this measurement, then you infer what's the redshift. And then you can compare what's the difference that you get if you make a spectroscopic measurement versus a photometric measurement. So basically, you have a very good population along the diagonal, and then you have 4% outliers. This is measured from the CFHT analysis. So there's still some scatter, and this is one of the main systematic residual effect in weakness measurement. But still, you can do good science with that. This is the cumulative redshift distribution of all the galaxies in CFHT, basically. So it's maximal at about 0.5, median at 0.6, something like that. And so now, after you have done your shape measurement and your redshift measurement, you'd like to have your model, right? So this is what you measure, your estimator. And this is your theory, and you would like to compare both. So in theory, you start with a power spectrum. So this is, it quantifies the growth of structure and the structure at different scales in the universe as a function of time. And it's a statistical object. There are very good models for that compared with simulations. And so this is basically, this is a calculation from a three-dimensional box of dark matter. Weak lensing is a projection effect in a light cone. So basically, you'd have to integrate over angles, so you get these angle factors. Plus, because it's source lens system, if the source and the lens are at the same place, the lens is not really lensing anything. If the source and the lens are sort of, if the lens is exactly at the center between you and the source, this is maximally efficient. So this geometry is all contained in the kernel, which I call the W. And the kernel depends on the location of the source, the location of the lens, and n of chi here. That's the curve I showed before. It's a distribution of galaxies as a function of redshift. Should have been the same name, but different names occur in the literature. So this is all the geometry term. This is the cosmology. To a certain extent, the geometry also depends on the cosmology, but the main parameters are the power spectrum. And then you do these integral over L over K, and then you have your model for psi plus, psi minus, which you can relate to psi t, psi r. So this is how you get your comparison.
So that's the correlation function of the shear?
Yes. So this is.
That's what you actually measure in the images.
It's one of I'm talking about today. Cosmic shear with this parameter. There are other estimators of cosmic shear, aperture mass, and you can also just measure the Fourier space or the power spectrum, the angular correlation. So this is, I just wanted to talk about that one because it's the one which was promoted by CFHT lensing. So this is This is the telescope sitting on the top of Mauna Kea in Hawaii. A little bit it belongs to us because it's a French, Canadian, and Hawaii telescope. And it's been there since 1979, so it's an old observatory. But then the camera is quite recent. It's a megacam, and it had all these UGRIZ filters. And then, so what this lensing did, this is a sort of picture of the sky. This is the galactic plane here. Here is the North Galactic Pole, South Galactic Pole, and the 4 blue squares are the 4 CFHT fields which were observed. The total area is about 150 degrees, and this is a zoom on these 4 fields, W1, 2, 3, and 4. So each of these fields were decomposed into pointings, and each of these pointings were observed in 5 color bands. Some color were missing, so there's a lot of gray here. But overall, that's the setup of the CFHT observations. And then from each of these images, we look for galaxies. We get the shapes. We get the redshift, and we get a bunch of other quantities. Not all of them are relevant for the cosmic shear, but they are for other studies you can do. But for cosmic shear, you need x, y position, P of z, that's the probability distribution of a given galaxy to have a given redshift. And then you also need the weight, which tells you how well you measure the shape, and then the shape components, E1 and E2. And from this catalog, which is public, so you can download and do your own science, we had a bunch of science papers. So the first section is, it describes a survey, describes how you measure the shape, how you measure redshift, how you did the observation strategy going from the image to the catalog. This is a cosmology paper, 2-point functions, testing laws of gravities, testing the impact of redshift contamination. There's also one which was recent here that showed it's a 3D lensing, basically. So they run a 3-dimensional sort of ray tracing, but in the data. And this is the map also, so I'm going to talk a little bit about that. But let's start with the first one here, because this is what I've been talking about first, the psi plus, psi minus measurements. So in blue, that's a psi minus. In black, it's a psi plus measurement. And the dotted lines are the best fit models. So this is in arc minutes, 1 arc minute, so small scales, 100 arc minutes, large scales. And then from this measurement, you want to get to the cosmology, so P of k. And then you can get error bars, contour plots. So these are 2 cosmological parameters, sigma 8 and omega m. That's the amount of matter, and this is the normalization of this power spectrum. And so weak lensing is sensitive to a combination of these 2 at the same time. So you can't really tell where you are exactly inside that banana. But when you combine with other probes, for instance, if you combine with the WMAP7, which depends on a different matter on these parameters, then you can get tighter error bars on these parameters. So this is where a combination of probes is really useful, is to have very small error bars. Yeah, so here basically what I want to show here is that sigma 8 is the amplitude of P of k, and in this equation here you have W, which depends on omega m. So it's right there's a degeneracy between sigma 8 and omega m. That's why you don't have a circle, but banana here. The answer depends on both parameters. So that was the first science I want to do with I want to present you with CFHT. The second one is mass map reconstruction. So basically, this is Poisson equation, which relates the mass to the Newton gravitational potential. And from the potential, you can take derivatives and solve for the convergence or solve for the shear. And what we measure in the data is the shear. Once you measure the shape, you're sensitive to the shear. So you can use the shear measurements and then reconstruct the Newton potential and then reconstruct the convergence. And the convergence is, so you see that's the Laplacian over 2. So it's related directly to the mass. So if you measure convergence, in some sense you measure mass with some prefactors. And this is a map of the W1 field, so it's the largest field in CFHT. The background colors are the mass, and the points are the galaxies which are in the catalog. And if you can do a cross correlation between the galaxies and the mass, and then correlation is really high. You can do the same with the voids. So you correlate the voids with no galaxies, basically, and then you have a strong signal for where the voids are. You can do 2-point functions, 3-point functions, and compare that to theoretical models. So here's what I'm showing here. That's kappa 2 and kappa 3. Kappa is the convergence. So you do these measurements, you compare to model, and then you can constrain what's the best fit model for that. I wanted to draw your attention on the error bars here. Sorry. What is this? Okay. So these are 1, 2, 3 arc minutes. It's really small scales. These systems are really nonlinear. So how do you get the error bars in a very highly nonlinear system? Well, error bars has many contributions. There's some from your instrument, some from your method, the photometric redshift measurement where it's not 100% accurate. But also the stuff is correlated. So you do measurements, you have a number of independent measurements. Some of them are dependent, there's correlation, and then there's this cosmic variance as well. And for this cosmic variance part, you need, and to measure the correlation, you need galaxy mock catalogs. So we use n-body simulation, which we populate with galaxies to create mock catalogs and measure the error bars in these mocks, which we add to everything else in quadrature to have these error bars. So mocks are really central to weak lensing analysis. And so in this figure, I just want to tell you that all the papers which are inside the Maron circles, they were calibrated against n-body simulations, which were run here at CITA. So it's a good promotion. So here are two future surveys. Well, future analysis. This is the RCS2 survey. The white patches here are different patches in the RCS survey. The survey is completed, but the analysis is ongoing. I think Howard Yee is one of the PI of this project. And then this is the kilodegree survey. This telescope is in the Atacama Desert. And this one will observe, the goal is to observe 1,500 square degrees on the sky. So it's a factor of 10 larger than CFHT. And this has observed 900 square degrees. So the surface of data is just 20 times larger. And what we need for these analysis is mock catalogs again. So I will spend a few minutes describing the mocks because this is my main contribution to these two projects. So I'm using an n-body code called QP3M, which is under development here at CITA. It's been going on for many years now. Has many applications. It's very fast, high performance, and it's running on SciNet, which is a few blocks from here. I have already run 500 n-body simulations. These are dumping on the fly 2-dimensional mass maps, 3-dimensional halo catalogs. We can't really store all the particles because it takes too much memory when you have 500 of these. It's too much memories. But we have a very good resolution of halo with 3 to the 11 solar masses. So this is where the sensitivity of your galaxies and your halos, that's sort of the lower limit that you need. So we have that secured. Once we have your n-body simulations, we run ray tracing code to see what the light, how the light gets modified as it goes from background sources up to you, going to the matter, gets distorted. So we want to simulate that. So we do a ray tracing calculation. Then we put galaxies in under these halos. So the background map here, the colors blue and white, that's the dark matter density, basically. It's a two-dimensional surface. Then the red circles are halos, which we find on the fly. And then the squares are galaxies, which we put in these halos with a halo occupation distribution. So I won't go into the details of that. But basically, this is what I would give to astronomers. And they use these catalogs. I just give them the galaxies, just the galaxies. And the shape of each galaxy is a contribution from a random number plus the shear created by the dark matter mass. So I construct these MUCs, I give that to the astronomers, and they calibrate their science against these MUCs. We also have a blind analysis, so have a few simulations where one cosmological parameter was different. So I'm asking them, can you recover that cosmological parameter? So what is the new value of sigma 8? Can you tell me what it is, just to know that your analysis is robust? And then there's one component which needs to be calibrated against data. So it's the weight, because in simulation, I don't have really shapes. I need to know how well can we measure the weights in the simulation. I don't have that. So I use the probability distribution from the data and feed that on the galaxy. So for each galaxy here, I draw a number of which corresponds to the size, to the weight, and then it goes in the catalog. So it's a simple operation. So then the MUC looks like the real data in the end. How much time do I have? 10 minutes. Okay, that's good. So I can talk about combined probes. So
Before you go into that, just in lensing alone, how does the accuracy of your sigma 8 measurement, or I guess vertical width of your slice, scale with the solid angle of your survey?
yeah, the error bar is a contribution from different things, right? You have the photometric error. It does not really goes better if you have larger area, because if you don't improve the method of photometric measurement, that part is not there. But the part which is the variance, this gets reduced. It goes as 1 over the area. So you have an improvement, but it's just one term which is improved. So combining probe is useful in the sense that some different probes of a large-scale structure depends differently on parameters. So you combine them, and then you can break degeneracies in parameters. This is when you combine them. If you cross-correlate them, there's an extra advantage that the noise in each of these measurements is canceled, because the noise of one measurement does not correlate with the noise from the different one. So you can really pin down sometimes better values of parameters, but it's harder. So here's the first detection of the galaxy lensing cross CMB lensing. So we have this light which is coming from the CMB, and it goes through the dark matter. The same dark matter, the same galaxies, it comes to you. So you can measure the CMB lensing from, so you measure the lensing signal from the galaxies where the sources are the CMB, and the same galaxy lens sources behind. And if you cross-correlate these two signals, you should get something. So here is the region called stripe 82. It's an interesting region because it comes from a defect in the SDSS telescope. So for a while, the SDSS telescope was only able to span in one direction and not able to span the whole sky. So it spanned there for months and months and months. And then so we have a very high detection and a region of a very high detection and good signals. So other people, other teams say, well, okay, let's observe there as well, because we can complement what what has been observed here. So ACT here is this is the Atacama Cosmology Telescope observing the CMB. So the CMB, the red rectangle is ACT. The green one is the CFHT stripe 82. So it's a CFHT telescope looking there as well. And this region, cross ACT, is giving us this result. So that's the first cross correlation measurement. It's a 3.2 sigma detection. So it's not, strictly speaking, it's more like evidence at this level. I think detection is above 5 sigma. But it is strong evidence that we have measured this cross correlation here. One of the problems with this measurement is that it's really, really sensitive to the redshift distribution of all your galaxies. And this is hard to get because it's photometric redshift measurement for some of them. It's a hard measurement to do, and the signal changes very, very rapidly if you change the redshift distribution. So if you get it wrong, your theory and your interpretation is wrong. So there is a lot of development which needs to be done in that field if we want to constrain cosmology. So far, we have detected the cross-correlation, but it's not useful at the moment to do strong and competitive cosmology. But that's the next step. So it's already a good thing to be able to do that. And the next step is to improve this measurement and do cosmology with that. So this is now it's a second kind of cross-correlation which we can do. It's also involving the CMB, but CMB light here sometimes passes through a cluster of galaxies, and clusters is filled with gas, really, really warm gas, and which heats up the photon, so the photon get scattered and gains energy. So when it arrives at the observer, the spectrum in frequency is shifted towards higher energy. So it goes from, say, the dashed line to a solid line here. So when you do a CMB measurement and you look at the spectrum in the sky, it looks like a black body. And then you look at some place and, oh, it's not a black body there. This looks more like this curve. Something must have shifted the frequency of the photons. And so you can reconstruct the mass of the cluster. It's called a SZ measurement, so you have Zeldovich measurement. And so you could think that you have a map of the clusters in the sky using this effect. And so gas here, this is warm gas causing this effect. And we think that warm gas traces dark matter. So if we were to cross-correlate this signal with the mass map we got from dark matter only, sorry, it's not dark matter only. The lensing signal is dark matter plus baryons. And we cross-correlate this with this signal, which is just baryon. The cross-correlation gives us only the baryonic component of this correlation. And we know that 40% of the baryons are missing. So maybe when we do this cross-correlation, we can pick up where the baryons are. And so this is the measurement which has been attempted, and I think it's successfully in some manner by Ludo and Norm here in this room, and Gary Hinshaw from UBC. And so this is a measurement of the cross-correlation between the Y is the Y-Compton parameter from the SZ signal and the convergence map. So you take the SZ map, convergence map, you Fourier transform, cross-correlate, and then you have this measurement. The black is the signal, and the red is a B mode. And a B mode is basically when you take your mass map from weak lensing, but before creating the map, you rotate all galaxies by 45 degrees. So that destroys your signal. So it's a good null test. And so this is what was shown here. So the bottom line here is that the difference between E mode and B mode gives you a strength of the significance of your detection. And here, this was, I think, a 6 sigma detection of the cross-correlation between these two maps. So it's an excellent news. And the claim here is that the baryon signal, the cross-correlation, it's significant even at 30, 40, 50 arc minutes. So you're looking at larger and larger scales, and you still see a cross-correlation between the baryons, between the two maps. So this tells us that, in some sense, the baryons are tracing dark matter up to very large scale. It's warm baryons, because this gas needs to be warm. So even though we don't see it as galaxies, we don't see it in just the SZ map because there's noise, when we cross-correlate, we see a signal to larger scales. So this is one step further in finding the missing baryons. I think from my understanding, one of the weakness of this measurement is the model. So the model here was, some say, oversimple. So there needs to be an improvement on this line to have a very solid interpretation of what the measurement was. And with future surveys, if we redo this measurement, then the error bars should shrink quite significantly. And if the model is even better, then we can learn about the missing baryons. So I think this is one of the very, very hot topics in cosmology. So this is my final slide. I just want to, I'm hoping that you will remember that for cosmic shear survey, you need the shapes, the redshift, and areas for the error bars. You also need mock catalogs. I use n-body simulations, but there are other ways to do mock catalogs, which I have not talked about. And then when you do cross-correlation and combine with different probes, you can shrink the error bars on the cosmological parameters, but the model can get tricky, so you have to better do it right. Thank you.
Thank you. Questions or comments?
Yes.
I had a question about the weights in the mocks, which is
Okay.
that you sort of assign them randomly. But I was thinking, why not put some sort of once you pick the intrinsic orientations and then you share them, is there a way to let the lens fit pick the weights naturally? Like, because you don't have, for example, overlap effects and so on, because you're picking the weights completely randomly?
It's not completely randomly. I might have gone fast on that. So basically, this is from data. This is the size versus, so the size versus the apparent magnitude. This is the weight versus apparent magnitude, and the weight versus the size. And so what I do is that we realize that the weight depends strongly on the size and on the apparent magnitude, and weakly on everything else.
And like the overlap, that's weak, a weak
Yeah.
dependence.
Yes. So what we do is that we construct these PDFs from the data, and then from the simulation, what I get is the apparent magnitude, because I know what's the redshift of the object. So I pick up the apparent magnitude. I use this relationship to get the size. I assign the size, and then from the size and the apparent magnitude, I get the weight. And then I roll the dice for wrong measurements sometimes. So if we know that, I don't know, 10% of the objects have something wrong, you have a zero weight because the PDF was wrong or there's an overlap or something, I roll the dice and try to preserve this quantity.
So I've been wondering, is it clear that these galaxies that sit around the same halo, let's say, aren't intrinsically aligned to some degree? And if it's not clear, could that upset your shear?
Yeah, so intrinsic alignment is one of the main contaminants of weak lensing measurements. I have not put, so basically what that means is that you're trying to get, you're doing 2-point functions of galaxies, and some of them reside in the same cluster, so they are connected by the tidal force. So they are aligned by the tidal force regardless of source and lens. So they are that's called intrinsic alignment, and you need to model that and take this out of your analysis or include that in your error bar. And so in this simulation so far, we have not included intrinsic alignment. That's the next step, because we're just building up something more and more realistic. So if we don't include intrinsic alignment, so just basically tidally connected the orientation of these galaxies, then we sort of apply the same error bars as we did before. So we model what we think should have been there, and then let's put a larger error bar for that. But the next step is to calculate what is the intrinsic alignment and put it there. And then something we could turn on and off and see exactly what's the contribution from intrinsic alignment. And nobody has done that before. So So on the cosmic frame. So that's one of the
So
next.
that's the question. How big are the boxes in your simulations?
It's 505 H inverse meter per
And
second.
your sort of spatial resolution or smoothing length or whatever is kiloparsecs or?
It's 500 divided by 30,000. So that's a few hundred kiloparsecs.
Yeah, okay. So it can't be the intrinsic language yet. Or it's going to be hard.
Well, there's a tail of effect. Yeah.